And that there are also different other related techniques which we have used in connection with so-called fluid structure interaction problems. And there I really want to mention David Nuschletten, who was formerly at King's College in London and is now in Michigan University, and his PhD student Max Balmus, and then of course again the Swedish gang Johan Hoffman. So really a lot of collaborators over the years who have worked with that are really grateful for all these collaborations. And also, I mean, I really want to make this also an open discussion. So if you have any questions at some point, just jump in, ask me right away, and then we can take up your questions immediately. Okay. Okay. So what I want to talk about is basically three things. So the first thing we will talk about is a little bit giving you a short introduction, motivation, and challenges when you want to design or when you want to use these so-called cut, or we call it cut finite or unfitted finite element methods. So why do we want to use it, and what are the challenges we are encountering? Then the second example I want to look at the certain class of unfitted finite element methods where we actually use overlapping meshes in order to kind of decompose complex geometries. And finally, I also want to exemplify how you can use these models in order to discretize, for example, so-called mixed dimensional problems, where you, for example, have partial differential equations which are posed both in a let's say in a 3D topological domain, but also then coupled to some partial differential equations on the boundary of this domain. Yeah. So those kind of problems typically occur when you have cell biology problem or two-phase flows. So where you have these mixed dimensional problems, and here we can use cut finite element methods at our advantage in order to present a unified formulation of those coupled problems. Yeah? Okay, let me give some motivation. So the main motivation of using CutFEM is the basic observation that the generation of meshes for complex geometries can be really, really complicated. Yeah. So what means complicated? Complicated in the sense that it can be computational demanding. Yeah. In order you have to use a lot of computational resources in order to generate this mesh. For example, on the left side here, this mesh, where you really have a lot of tetrahedrons which you have to generate for this geometry. Yeah? So that is something which can be computationally quite demanding. And especially also, maybe you don't really have the entire geometry at once, but you have only different parts, for example, the wing or the main body of this airplane, and then you have to set together, and then really generating like a so-called watertight mesh for this entire airplane can be quite challenging. Another topic is, for example, when you want to generate geometries, for example, from biomedical imaging data. For example, here we have this is a vessel, a blood vessel with an aneurysm here on top. And then, of course, for example, doctors want to know, okay, if I have this blood flow, is this aneurysm here, is there a risk of bursting or not? And we can answer these questions, or at least try to evaluate these questions or evaluate this risk by doing computational fluid dynamic simulations. But first of all, we have to generate a mesh for this geometry, and that can be also quite time consuming because you have to get from the medical data, and then you have to generate a surface mesh, and you have to make it a high quality surface mesh, and then you have to compute a high quality volume mesh. So there are really several steps involved in this entire mesh generation pipeline, and that can take you easily between depending on the problem, between hours and days or even months to generate a proper high quality 3D mesh for your simulation. So mesh generation is quite challenging, and what we want to do with CutFEM is basically ease this burden of mesh generation. I want to give you also a few examples where this might be come in handy. Yeah. So two examples or two application examples the development of our methods are motivated by are the following. So one is something which is called microfluidic devices. And microfluidic devices are devices usually typically on the micrometer or even nanometer scale, and where you want to use to manipulate very, very small fluidic particles. Yeah? For example, you want to sort cells, usual cells, cancer cells, or you want to sort droplets according to sizes, things like that. And so here I show you a simple example, which is a schematic of a microfluidic device where you want to sort droplets according to sizes. And what the main idea here is that you have one particular fluid carrying these droplets, these with the different sizes, and they have another fluid coming from the top, with carrying some surfactants, as a surface active agent. So you can, for example, think about soap as a typical example of a surface active agent. Then those will then, for those droplets which come in contact with, let's say, the blue fluid, the surfactants will assemble around the surface, and then they will actually manipulate the surface tension, and by the manipulation of the surface tension, these larger droplets will actually rise and be moved into the blue fluid. So that could be in a device where you can sort droplets according to sizes. There are really many applications of these kind of. If you break this system down, what you actually get is basically a two-phase flow problem, incompressible flow problem, described by the Navier-Stokes equation. So you basically have a Navier-Stokes equation of this type here for both the blue fluid and the yellow fluid. And even for the purple fluid here in between. But what is really interesting is that you have different viscosities, you might have different densities. So those are, of course, densities and viscosities are then depending on which domain you're in. Are you in the blue domain, in the yellow domain, or in the purple domain? So, and then between those, at this interface between these two fluids or three different fluids, you typically have also so-called interface conditions, and those interface conditions look typically like this, so you know that the flow velocity should be continuous, so that is here the jump of the fluid flow, and then you have also something is a surface tension, this is here the surface tension, so the jump in the surface or the jump in the fluid stress, basically, so it's fluid stressed. The fluid stresses is related to the surface tension acting on the interface between different fluids. So that is will be typically, and here we have a typical example of an interface flow problem. And additionally, and that is, of course, these kind of equations are actually posed in, let's say, in a three-dimensional domain when we're talking about a 3D fluid device. So you have a three-dimensional domain. But additionally, we have these surfactants, and these surfactants here, they will be transported within the fluid, but then they will actually accumulate at the interface, basically here at the interface of, for example, the droplet. So that means that these surfactants are transported both in the blue fluid, but also along the surface. And this is a typical example of a mixed dimensional problem, because then you get basically an advection diffusion equation which models the transport of the surfactants, and you have these advection diffusion equation both in the blue domain, which is like the bulk, but also on the surface of this bubble when these surfactants are accumulated. So in that sense, you have a mixed dimensional problem because it's on the surface, on 2D surface and a 3D bulk. So, and that is very interesting, right? So, because now you have moving domains with different physical properties, and you have a mixed dimensional system where you have PDEs on domains of different dimension. So, secondly, another motivational example is here the flow and transport of so-called porous media. So you can, for example, think about your brain as a porous media, but you can also think about if you want to, for example, search for oil or water. So you have to know what kind of properties, mechanical and fluid dynamical properties the ground has you're searching in for for your oil or for your water, and that is then typically described by a porous media. And quite often within these porous media within this porous media, we have something like fractures. Yeah. So, for example, if you going from one earth layer to the next, there might be a small space in between those layers, or you might have even a very, very small thin layer of different material or so. So all these structures then can be typically described by large-scale fractures. Yeah? And what you then have is some porous media here with some certain physical properties here. You have another domain, another 3D domain, let's say, with certain physical fluid flow properties here. But then you have this fracture in between. Yeah, that is something, since it's so thin, yeah, also in compared to its length dimension, you will basically consider it like a two-dimensional surface somehow embedded into the three-dimensional porous media bulk. So, and then if you, the equations are not really that important. Yeah? So here we have, for example, Darcy law, basically Darcy's law in both domain of I and some coupling conditions. And when you can then do some dimensional reduction, yeah, which leads you then to a so-called surface bulk problem. So don't pay too much attention here to all these equations. But what is important is that we have now basically a Darcy flow, yeah, a Darcy flow in the bulk domain. Yeah? But additionally, we have also something which looks like a Darcy flow on the surface with certain coupling conditions. Yeah? But that is, again, an example of a three-dimensional, with a PDE posed on a three-dimensional domain, coupled with a PDE coupled on a two-dimensional domain. Yeah? So it's, again, a mixed-dimensional problem. Yeah? And all these different problems, so now we have quite a few challenges. We have moving domains. Yeah? How do we can handle this? And these moving domains can really undergo very large motions, because the bubbles really going through this entire device. Yeah, or imagine if bubbles, for example, merge or split off. Yeah, so we can give large motions, even topological changes, and we might also have the problem of coupling different dimensions together. Yeah, so that is also these main motivations for these finite element method, for these cut finite element methods. So what is now the idea? Well, the idea is that those unfitted finite element methods, that they can actually reduce the burden of mesh generation. And the idea on that we can do by different different related ideas. So one idea would be, for example, using overlapping meshes. And here's the idea, very simple, just to simplify that, is that, for example, if you want to change geometries here, for example, different angles of this wing, this 2D wing here, what you can do is that you, for example, could imagine that, okay, I basically provide a mesh for my wing once, yeah, and if I then want to modify the overall configuration or setup, I will just change, for example, the rotation angle, yeah, but I'm using the same mesh for the wing and the same background mesh behind, yeah, and just adjust, yeah, in quotes, I just have to somehow couple those two things together, yeah, but I don't have to remesh. And so every time I change the geometry configuration here, I don't really have to remesh if I mesh the background independently of my wing geometry. So that would be, so one idea would be overlapping meshes. Another idea would be if we, for example, look at embedded interfaces like in the porous media. So that would be again a schematic drawing of a porous media where we have our two-dimensional blue domain, and then there's this fracture network painted by these red lines. So what can we do about that? Well, again, the idea would be that we don't really mesh it conformly with respect to these different fractures, but we again somehow provide or try to devise a method which is able to handle those methods or able to handle these problems, even if the mesh you're working with is not really fitted to the geometry. And then, for example, in the case of geological data, there's quite a lot of uncertainty. You don't know exactly where certain kind of fractures are, or you might want to look at let's say a random distribution of those fractures. So you want to be able to quickly change those geometries. And then again, the idea is then that you can quickly or seamlessly change between different fractured networks by keeping the same background mesh. Yeah? But the question then again is, how do I actually couple those problems then? And the third problem is also with respect to moving meshes. So for example, thinking about these bubbles or these droplets moving through this fluidic device. Yeah? Here we have maybe a rather simple geometry to start with. So remember those droplets in a microfluidic device, it's kind of more or less a rather simple geometry, but they might move quite a bit. Yeah? And then the question is, okay, when we have such a moving interface, how can we represent that? Or how can we devise a method which is capable of following this? And there exists quite a few methods, of course, out there, which using fitted meshes. But here we really want to look at what kind of flexibility we can gain from this unfitted approach, where the background mesh is not really here, as in this example, it's not really fitted to this surface between, let's say, oil and water. So that are the main motivations behind it. But of course, the question is, now, if we don't really have a fitted mesh here, how do we actually make sure that when we couple those problems, so for example, if we have, let's say we have oil here and we have water here, and we have, of course, different physical properties, different viscosities, different densities, how do we make sure that we can then couple those problems properly along those embedded interfaces, which do not really fit to the underlying mesh anymore? And how can we do that without, let's say, for example, deteriorating the order of convergence? By how can we make that still maintaining the good properties of a standard finite element method, for example? So that are the main questions. Or even if you just think about the boundary problem, the question is, if you have such a boundary here, how do you impose boundary conditions now if the boundary is not actually a part of your mesh? So this boundary is not really a part of it's not really represented by some kind of boundary mesh. It's this description here of the interface. It's basically independent of the background mesh. So how can we do that? And here there's a very nice idea going back to Nietzsche, and I will just explain Nietzsche's method first in a fitted mesh setting, so where the boundary actually fits to the mesh, and then we will talk about how we can generalize this idea in order to treat unfitted methods. So if we know how is Nietzsche's method working, and if you, as I said, if you have any, I'm only seeing my screen now, so I don't know whether there are some chat messages or anything. If you have any questions, just interrupt me and ask me. Okay, so it should be an open seminar, and I'm really happy to answer your questions. So how is the Poisson problem actually defined? Well, here the idea is or how's the Nietzsche method for the Poisson problem? Here the idea is that we start with a simple Poisson problem with directly boundary data. So we have U is equal to G on the anti-boundary gamma. And how do we derive usually a finite element method? Well, usually what we do is that we multiply those functions here with the test function. We do some integration by parts. But now what we're doing is that the function space we're going to use, they won't take into account the actually boundary conditions. So in standard finite element methods, boundary conditions are basically built into your function space. So what we do here now is that we try to find the UH in some finite element space, some discrete space, built from those meshes here, which is really now a part of H01. So only gradients exist in a weak sense, but we don't say anything about the boundary conditions of those functions living in H1. We don't say anything about that. So, and what we require is that the typical finite element formulation, so that A of UH, VH is equal to some right-hand side by a linear form L of VH. For those, that should be a capital VH, I'm sorry for that. And then the question is, how is the bilinear form and the linear form looking like? Well, the idea is now that, okay, we multiply with the test function and we do the integration by parts. So then we get the usual gradient UH times gradient VH term. But then since we don't have any requirements on the actually boundary data, we get also through this integration by part, we get also this term, this consistency term here. We get a gradient of UH.n, comma VH on the boundary gamma. Now that pops naturally up from the integration by part. Okay, that is nice. So that would be our first try. But then what you see is that this that formulation is not symmetric anymore, right? So because if you're now changing VH with UH, you don't really have a symmetric formulation. But we know that our Laplace operator should be actually a symmetric operator. So in order to repair that, what we can do is that we can add a so-called symmetrization term. So we're just switching UH with VH. But in order to make it consistent, we have, and the nice thing is then here with this UH, we know the data of UH on the boundary gamma, right? Because that's exactly our boundary data given here in this second equation. So in order to make it consistent, we have to subtract the same term here, on the right-hand side, and this time just with UH replaced by the boundary data. So what we actually add was something like the normal flux here times UH minus G. And remember, UH minus G should be 0, at least in some weak sense. So adding this term makes this formulation still consistent. So the true solution will actually satisfy this kind of relationship still. And then we also have to add something which you can regard as a penalization, or maybe even more like stabilization. So what you also add, and that is for the purpose of guaranteeing that you actually have a stable method. So what you're also adding is a penalization with this certain kind of H scaling here. And what you see is that what you again have added is something, a boundary term, UH minus G, which again is a consistent term. UH minus G times V divided by 1 over H. So that is basically the term you added. So that is the entire Nietzsche formulation given in, I think it was in 1971 by Nietzsche. It's a very nice formulation because it's a consistent formulation, symmetric, and a consistent symmetric formulation which gives you optimal convergence order. So previous methods, as before 1971, were basically based on some penalty approach, which were not really consistent, and then you didn't really retain the classic convergence order you would expect from a usual standard finite element approach. But this method is very nice because it really retains the classical order you would expect from a standard finite element method. And now the first idea of going from fitted meshes, we're going now from fitted meshes to unfitted meshes, and the idea is very simple. We can just keep this bilinear form and linear forms here as it is. The only thing which we're switching out is now the background mesh. So now we're just having some background mesh, and you see it's not really fitted to the geometry anymore, but that does not really hurt us because all those formulations here, the incorporation of the boundary condition is not happening point-wise as in the classical finite element method, but it is basically done in a weak sense through the addition of those integrals here, of the boundary integrals. And these boundary integrals, of course, does not really change any meaning just because you're going from a fitted to an unfitted mesh. And what you basically are doing now is that you formulate, you take the finite element methods developed on all those, or basically post on this entire background mesh, and you use those functions in this variation of formulation. That's the only trick. But remember, so somehow this bilinear form here, it doesn't not really see the entire background mesh. The bilinear form and the linear form still only sees the omegas and the gammas here, and that's where the trouble comes from. So what do we do? What we actually do is that we quite often talk about something like a so-called active background mesh, and that are those elements, which are basically in some sense intersecting omega. So this active background mesh are those elements, either they reside completely inside my domain interest, or they are somehow intersected by the boundary where I'm supposed to impose my Dirichlet boundary condition. So that is actually the mesh we're interested in. And on that mesh, we just define our standard finite element functions as usual, but then we're solving this kind of variational problem here, this Nietzsche formulation. So that is the basic idea. And then there are some troubles arising at the horizon, and there you can say that there are two main challenges, at least in this simple formulation. So the first thing is something so certain inequalities which we typically use as mathematician in order to provide a stability and convergence analysis. Those equations that do not hold anymore. So what we typically have is something like here. Also, what we need to estimate in these Nietzsche formulations, typically, in order to provide, for example, discrete coercivity, is to provide an inverse quality or inverse trace inequality, if you want so, of this kind of form, which relates the normal flux here, n dot gradient u, with some h scaling here, which relates this normal flux on the boundary where we're imposing our Dirichlet boundary conditions weakly. We want to relate this guy here with the corresponding gradient term, but now, and that's the main difference, not on t, but only on the physical part, on t intersected with omega. Because we have to somehow, I mean, our problem a priori is only posed on omega, so we cannot, we have to consider here the gradient only of this guy here in the physical part t intersected with omega. So in this drawing here, so the gray area is basically the physical area, so corresponding to the omega area here. So the gray area, we are actually inside our gamma. And here with this example, you can already see that, okay, here I have quite a large flux term, because this here the interface gamma intersected with t scales basically like h, while the area here, this little physical part of my domain, because we don't really take the entire triangle with us, we only take the physical part with us. So that is t intersected with omega, and you see that the closer I move gamma towards this line here, the smaller this area get. So there's no chance that I have this kind of inverse inequality here with a constant which is bounded, with a constant which is actually stays bounded. So this constant would actually blow up. So that's a bad thing. So that is one challenge which really arise in the stability properties of these Nietzsche formulation for unfitted finite element methods. And the second is also when it comes to solving problems. For example, if you have a linear algebra solver, you have an iterative solver, you're quite interested in the conditioning number of the resulting linear system. And if you have such an example here, so for example, if you have an intersection like this, so you see again the gray area is just the physical part. And remember, my bilinear forms, what do they integrate? They integrate over omega and they integrate over gamma. Nothing outside of my physical domain omega. So that means if you, for example, look at a standard P1 as a first order finite element method, you would gain 1 degree of freedom, which is associated with this upper node x here. And if you then look what kind of contributions you get, well, the surface contributions are very small because you have only very small surface parts here. The volume contributions are also very small. So in total, the entry in the matrix system related to the degree of freedom which is resided here, this entry will be really, really small compared to all other entries. And you see if I just move this boundary gamma here towards this to this node, what you basically get is a non-invertible matrix anymore, because this degree of freedom won't have any contributions at all in the limit case. So that's another problem, that you get a system which is not really well conditioned in terms of the matrix number. Okay, and here the idea, and that is really one of the main ideas of CutFEM finite element method, namely how to repair those properties. And it's quite a far-reaching idea, which originally has been used for the Poisson problem, but now it has been used really to surface problems, to really a lot of different problems. So what is the basic idea? Well, the basic idea is that and these last two cases we discussed, yeah, that the bilinear form A is only seeing the physical part. It's only seeing omega, and therefore it does not really provide enough control over our finite element methods, yeah, or finite element discrete functions. They are defined here, right here, also on the outside of this area, all this yellow part here. But the bilinear form A does not really give us any control about this part. Yeah. So no matter what happens here outside with my finite element function here, the bilinear form A won't see that at all. That is really the problem. That's where this ill conditioning actually comes from. So now the idea is that we somehow want to restore that. How do we get, what we want to have is that we want to have to control over our finite element functions, but not only in the physical part omega here, but on the entire active mesh. Yeah? So we somehow want to regain control over those finite element functions. And that is a very basic abstract idea of the ghost penalty. The ghost penalty works like this, or that's the idea. So whatever norm you're interested in, whether it is, for example, an L2 norm or an H1 norm or certain other norms, yeah, whatever norms you're interested in, yeah, you somehow want to extend the norm or the specific norm you're considering from the domain omega, which is just the physical domain, to the entire active background mesh. So that is the idea. But you want to do it in a smart way, because if you do it, let's say in a dumb way, then you might destroy, for example, the convergence properties, or you might have a very large inconsistency of your problem, which destroys then the nice convergence properties of the standard finite element method. So the idea is here that we somehow want to regain control. We want to gain control over the finite element functions in a certain norm on the entire active mesh by augmenting the norm, which is only defined on the physical part, by some so-called ghost penalty terms. Yeah, and these penalty terms or stabilization terms are called ghost penalties because they will basically also act outside of our physical domain omega. Yeah, in order to make sure that we still see our finite element functions. And since they are kind of acting outside the physical part, they are called ghost penalties. Okay, so that's a very abstract main idea. And the question is how to realize that. So there have been, and that is, so the idea of the ghost penalty first came up in some seminal papers in 2011 and 12 by Burman and Hansbohr, and since then it has been that was really for the Poisson problem, and since then it has been really developed in a lot of different papers, different extensions to different kind of problems, to overlapping mesh problems, to Stokes, from Poisson to Stokes to Navier-Stokes problems, even to partial differential equations on surfaces. But this overall idea of somehow augmenting our norms in a certain way so that we can regain control over our finite element functions on this active mesh, that is really like a very powerful idea. Probably. So the overall idea here is that I will also give you a couple of examples on how these so-called ghost penalty works like. So the very simple idea is here now that we're taking our Poisson problem, we're taking our Nietzsche formulation for this unfitted finite element method, and now the only thing we have to do is to augment it with a certain ghost penalty term, which I call JH here now. And how does it look like? Well, you see, so yeah, so what we get here is in the simplest case, that's really the simplest case of first order. If we have first order finite element method, then what you add is what you do is that you basically add a jump term. So that is here the jump of the normal fluxes along those green faces here. That are the terms. So if you're familiar, for example, with the continuous interior penalty method, it basically looks like a continuous interior penalty method. But you're adding those terms here only along those faces, which belongs to elements intersected by this boundary gamma. If you do that for first order element methods, then you can prove that you have a stable formulation which is really discretely coercive, and that you get optimal or a priori error estimates. Yeah. So I will just give you a few examples how you can use that. So one idea is, for example, when we're getting back to these aneurysms. So just to recall, what do we usually do if we really want to do fluid flow simulations? We usually have to extract first the surface mesh from biomedical image data. That is usually kind of a rough surface, not of high quality. We have to make it a high quality surface then. And then afterwards, we have to do a volume triangulation. And then we have to do a smoothing again in order to make it a high quality mesh. That can really a lot of steps here. So with using the Nitrous method, what you can basically do is that you just extract a low quality surface mesh, and then you throw that into a background mesh, a structured background mesh, which is easy to generate, and then you're using a Nitrous method, you're using the finite element methods post basically on this active background mesh, which are kind of built up by these elements, making this kind of Lego brick type aneurysm here. So those are the elements belonging to the active mesh, and you're using those finite element functions in order to propose an unfit or a cut finite element formulation of the Stokes or Navier-Stokes problem here. And then you can say, for example, easily compute the flow in this aneurysm without even generating like a proper 3D triangulation, or without even caring about the mesh quality of the surface mesh. So the main point here is that that surface quality here, or the surface mesh, can be rather bad in the sense that you can have stretched surface triangles, or you can have a very acute angles here, because you don't really formulate any, or you don't define any finite element functions or discrete function on those particular elements, because the finite element functions, they are really defined on a very nicely structured background mesh. So all the interpolation properties and approximation properties are not really affected by the surface, by the quality of the surface mesh. The only thing where this surface mesh is going into in our game is really when we do the integration of those functions. So the surface mesh will be only used for integration, but it won't be used to define finite element functions. So the surface of the aneurysm is basically our gamma and our finite element formulation. Let me see. When did we actually start, Stephen? Was it a quarter past?
We started quarter past, so it's quarter past, so it's fine.
Yeah. Okay. Great. And I have until 2.
2:20 is fine.
Okay, great. So I probably have to, but I just want to spend a little bit of time on the actually foundation, and then I can maybe skip quite a few details later on, just giving you the flavor of the idea. So what we can do here now is that we, for example, can prove easily theorems. That is really the simplest one. We have different variations of this, but what you, for example, can prove is that, okay, for the Stokes problem, and Jarle did, for example, something similar for the Brinkmann problem in his thesis. So what you can do is that we can prove optimal a priori error estimates, for the Stokes problem, and they look basically exactly the same way as in the classical case. But the important thing is here that those norms, or the constants which are involved in these a priori error estimates, they are not really impacted, or they are bounded above by a constant which is completely robust with respect to the cut configuration. So it doesn't really matter how the aneurysm geometry is located or thrown into our background mesh. We won't have these but even if you have like bad cuts, we discussed 10 minutes ago, these bad cut situations, even if we have these situations, it won't affect the accuracy or the robustness of the method because we have added those ghost penalties, and those ghost penalties will take care of all these bad cut configurations we discussed earlier. So that's very nice result. So, and that is kind of the theme about these cut finite element methods. So what we want to do, we want to provide error estimates or condition number estimates and things like that, which are all completely independent of how the boundary cuts the background mesh. So that is only and that is of course particularly important when we are passing to moving problems, because when you have moving problems, there's no guarantee. You don't know where your domain is going to move, and you're still keeping the same structured background mesh all the time. So you really have to have a structure. You really have to have a robust method to make sure that that your temporal discretization is actually giving you reasonable results. So just for illustration, I have here a simple example, where I solve the Stokes problem, basically within this domain here, and that with a given background mesh. And what you can do now is that we, for example, can shrink this domain here, and then what you see is that this domain, this degree of freedom here and this degree of freedom there, they contribute less and less to the overall matrix system. So an example, in this kind of case, it would be extremely ill-conditioned. So if you're now looking at the conditioning numbers, it really get very ill-conditioned. So let's look at, and what we have done here is now that we have plotted, the conditioning numbers for each of these cases here against a certain parameter which measures how close we are to this extreme case. If we look at this, what you see is here, and this delta is basically measuring how close are we to the extreme case. And what you see is that if we don't do any stabilization at all, then the conditioning numbers actually really exploding. It goes from 10 to the power of, let's say, 500, something like that. Maybe 500, goes from 500 up to 10 to the power of 8. If you don't do any stabilization at all. And I mean, if you want to use an iterative solver in a 3D case, for example, for a 3D flow problem, you're lost here. So there's no chance that you actually can solve this problem without doing anything special. So, but if we're turning on those penalties, that is, and those penalties are turned on by increasing here a certain stabilization parameter, then you see that you're basically getting a very good robustness. And here for this case, you're getting really almost a complete flat line. Of course, the overall conditioning number will be a little bit higher, but at least you get complete robustness here. And at the moment you have complete robustness, you can also thinking about, okay, how can I actually solve that in an iterative way? Because if you have a robust system and you design, for example, a preconditioner for this, then you can also ensure that if a preconditioner works in a certain case, it will probably also work in other cases. So it won't be affected by the cut configuration either. Just give you a quick example of how to use that for overlapping meshes. So here again, the idea is is kind of the same. You're having a domain and you decompose it into two domains, and you make the Stokes problem on this entire domain into two Stokes problems which have an interface condition, which is then given like this. And this interface condition is basically treated exactly the same way as the Nietzsche condition. So it has been already done for not overlapping meshes, but with an unfitted interface, very early by a nice paper by Giraud, Rivière, or Wieder in 2005. And then later on, we have used really ghost penalties to show that you can also treat the general case. So what we can do here now is that we, for example, have this kind of configuration. So we putting some mesh on top to describe the one domain, and then we measure the background mesh with another domain, and we don't care about how this is actually fitted, whether it's fitted or not at all at this at the interface, which is now made up by the boundary belonging to T2. And the formulation is not really that very much important, but the only takeaway is that you can do it exactly the same way as with Nietzsche. So again, you're getting some flux formulation here. You get these flux terms we have seen in Poisson. you're getting basically the symmetric term as in Poisson, and you're getting some penalization. And here now we're penalizing basically the jump of the solution, yeah, right? So the jump of the solution should be 0. And that is what we're penalizing here again. In the Poisson case, we penalized basically U minus G. And here we basically penalizing that that's the solution of the one side of the interface minus the solution of the other side of the interface. That should be basically 0. So that's what we're penalizing here. And again, now, again, we can adding some ghost penalty terms here in this scenario as well. They looked a little bit different, but the idea is, again, that we augment our bilinear form so that the resulting energy norms or norms we wish to control, those norms give us control over the active meshes and not only the physical domain. So here in that, for example, in order to gain control about for my Stokes solution here, on this background mesh, yeah, you remember, so even the light blue elements will be involved in describing my finite element solution, yeah. In order to gain control about those terms, what we're adding is a ghost penalty term, and this ghost penalty term is mainly evaluated on this kind of overlap region between the lower background mesh and the upper overlapping mesh. So this just another instance of a ghost penalty term. And then if you want to do that, if you want to show that it's actually giving you nice a priori error estimates and conditioning number estimates, you have to do the mathematical analysis for that. But we have kind of a framework which allows you to go through these examples and through these different steps and kind of verifying that, okay, if I have this and this kind of property, then I get coercivity. If I have this kind of property, then I get optimal interpolation estimates, or if I do this and this, I get proper conditioning number estimates. So, and how can we use that? We can, for example, use that in a fluid structure action problem like this. Like this, yeah. So the overall idea is that we have a structure here that's a solid structure. And then the green and the blue area is basically flow around the structure. And what we now simply do is that we start with some starting reference configuration, and we provide 3 meshes. Yeah. So the first we have a background mesh for the fluid for the main part of our flow domain, and then we have a green mesh. Yeah. And this green mesh is basically a small part of the fluid domain around this solid structure, and the solid structure is now meshed by this red mesh. Yeah? But the thing is that we have now here a nice fitting mesh between the overlapping fluid mesh here and the red structured mesh. So imposing boundary conditions or interface conditions, for example, translating stress from the fluid flow domain, which is exerted on the mesh on the solid domain, that is quite easy here because now we have a fitted domain. But the idea now is that we, of course, can move the structure here. And then when we're moving the structure, we're only moving this little green flow mesh here. We don't have to move the entire blue mesh. We only have to move a little part of this mesh. And then the coupling between the 2 fluid domains, between the blue one and the green one, is again done by these overlapping mesh formulations. So that's where we couple these flow problems. So what we can do now is, for example, doing a standard Fsi problem. And the idea is very simple. We solve the fluid flow problem. We solve the flow problem. That's, for example, the Stokes problem. The Stokes problem. So of course we have some certain interface conditions. And that are just simplified interface conditions, meaning that you have some kinematic interface conditions at between the flow and the displacement of the structure at the boundary. It's not so important what they are actually are at the moment, but the main point is that we can easily translate them. And what we can do now is that, for example, we start with some configuration flow, some 2 configurations of an overlapping mesh, a background mesh, overlapping mesh. We compute the flow solution. This will give us some boundary traction. With the boundary traction, we can compute the force of that gives us the forces acting on the structure, And with that we can compute the displacement of the structure, and the displacement of the structure will then give us boundary displacement, or give us Dirichlet data, and tells us how to deform the green mesh around this, the green flow mesh around the structure. And then and with that, solving this problem, we're getting another configuration, overlapping mesh configuration, and again solving this flow problem, and we do that until convergence. And that's very, very nice algorithm, and also converges nicely. And what you can do then is, for example, you can easily arrange for different geometric setups, configuration here. So we have here one wall or valve in one configuration, but we can easily just rearrange, just twist it by a certain angle. It does not really have, we don't have to remesh at all here. And then we're solving our fluid structure interaction problem. And what I do show here is it's basically the velocity or the streamlines on our flow, and you see that you have a very nice transition from the velocity solution on the outer part to the flow solution in the inner part, right? So those are actually, by construction, they are not continuous. They are only weakly continuous because of this Nietzsche formulation we're using. But you see that you get a very nice transition. Same also for the pressure. And when you're doing the other geometric configuration, you get seeing streamlines of the outer mesh solution nicely translates into the streamlines of the inner mesh solution. So it's a very nice algorithm. And that can also then be used, for example, for a moving mesh problem. So for example, if you have a wind turbine or a ship propeller or something like that, right? So you have really a lot of rotations here, and that is usually a killer for standard mesh, algorithms, because of this large rotation and large deformation than on the background mesh. But with using these overlapping mesh methods, the idea is really that what we can do here is now that we can mesh the domain omega 0 independently of the domain omega 1, and then we just translating, not translate, but we're basically rotating the mesh for omega 1 here very easily, and while we're keeping the mesh for omega 0 fixed. So, and that's a very, and again, the coupling between the different meshes here is again happening through this overlapping or cut finite element formulation. So that is, for example, a very simple setup here. We have the nice propeller. It is meshed independently of the background mesh. That is that. And now we can start rotating for this little propeller over here. And so I probably have to switch now. Let me see to this little guy over here. So let me see. Do you see this? Do you see my video?
Yes.
Exactly. So that is here.
Yes.
That is very simple formulation. The nice thing is here that you can, I mean, I don't know many how rotations, but usually with a standard finite element mesh, after a certain angle, you have to kind of remesh, or you do something clever because the background mesh or the outer mesh would be deformed too much by this rotation. But since you can rotate the inner mesh independently of the outer mesh, you can just keep it going for forever, and there are not any robustness problem or something like that at all. You can also use some collaborations. Let me see. No. We have also done that together for some synthetic examples where we looked at 2D, also like a mock-up 2D hard valve. It's a different formulation of how we handle the overlapping mesh part, but again, the main idea is that we're using overlapping meshes. Yeah, and then here we have so the part down here you have a meshed version where with the mesh, really the entire mesh has to follow this fluid structure, the structure for this little valve here. But up here, we provide a certain overlapping mesh around the structure, which is allowed to move freely with respect to the background mesh. So if we're looking now at the example, let me see, do I have that here? So that is the overall idea, that it's moving like this. And you see here, you in the upper red mesh, you basically see any kind of mesh deformation. I mean, of course, it's a little bit stretched here and there, but it's overall you keep quite a nice mesh quality. While here you see you really have to have a much finer mesh, and also the mesh quality at some point actually gets quite bad. So, and when you do that, you can do the simulations, and you see, so that is here for not too large valve deformation, but you see that you basically get very nice agreement of these overlapping mesh methods, or a partition of unity method is here, and so the upper part is again an overlapping mesh kind of method, while the lower part is a classical mesh method working with mesh deformation. Okay, so now with that, so I'm just wondering, should I use maybe 5 minutes to tell a little bit about how to use that for surface problems, or should we just?
Yes.
Okay.
Just
so,
5 minutes.
Yeah, exactly. So I won't tell you too much. Just make an outline of the idea. Now, what is the main idea? So we're just looking at in the simplest case of a mixed dimensional problem, motivated by those examples we had in the very beginning. And what we have here is then basically a Laplace equation, or a diffusion reaction equation in omega, and we have a diffusion reaction equation on gamma, and we have like coupling condition between those two solutions. But really the important point is that you have an additional surface PDE here to solve. And the question is how to discretize that. Well, there has been some nice work in that, especially by Elliott and Rana, who looked at fitted finite element formulations. And the idea is then just you provide a weak formulation for both parts here, and you can naturally incorporate your boundary, these interface conditions here on gamma. But then again, you have to have a fitted mesh, and that is something we want to avoid because the domain might move quite a bit and so on. So the idea here is again that we're using a background mesh, and now we're using this background mesh for both discretizing the bulk problem and discretizing the surface problem at once. So the idea here is that in a very simple setting, how do we discretize the bulk problem? Well, we have for the bulk problem, we're taking this background mesh, which is consisting now of all the green elements. That are those elements which will define, or which we use to represent the solution in the bulk domain. And then we have a bulk equation, a bilinear form for the bulk equation, but in order to make sure that all the things like a priori estimates, stability, coercivity results, in conditioning number, and so all that still holds, we will again add a suitable design ghost penalty term. Here it is called SBH. And now the question, how can we do that with the surface problem? Surface problem is exactly the same. Again, we identifying those elements which are intersected by the domain of interest. And here, since we're only looking at the surface problem, we're only taking into account those elements, gamma, those elements here, which are actually intersected by my surface domain. And what I do now is that I take the surface equation here, and I again build up my finite element space which is defined by those elements, so these green elements. So that is the active mesh for my surface problem. And again, I just use the naive variation formulation for the surface problem, but I have to augment it with a certain penalty of certain stabilization term, in order again to make sure that I have robust approximation and well-postedness of properties. How those and those ghost penalties here look, of course, look different for the surface problem as compared to the bulk problem, but the idea is always the same, that we somehow extend a norm. So what we want, for example, to do here now is that we don't really want to control the L2 norm of my solution only on omega, what I do want to do is to control, for example, the L2 norm of my finite element function of the entire background mesh. And then the question is how to extend this control from the surface to these active background mesh. Yeah? And so you have to design certain stabilization, certain ghost penalty terms for that. Yeah? And when you do that, it's not really important. Let me just quickly skip that. I mean, I don't, but the overall idea is then simply that you have these function spaces, and you have these function spaces, you always have a naive formulation, which you would get anyhow, no matter whether you have a fitted or unfitted formulation, yeah? And you always have to augment it if you have an unfitted situation with a certain stabilization form. So if you're interested in how to design those, I can talk about that quite a bit. So just to give you an example, yeah, the stabilization terms looks quite different. Yeah. So for example, for first order elements, so now we're just talking about the surface problem. Surface problem, as I said, are slightly different and bulk problems. And there you have different choices here again of how to design those ghost penalty terms. There are different variations. Yeah. But the overall, let's see, the overall idea here is that we, again, just to give you a flavor of idea, what do we have? What we can do is we prove the following: we can control the L2 norm of a finite element function on the entire background mesh here by using a certainly properly scaled L2 function on the surface, but we have to augment it again with a stabilization term, and the stabilization term in here is just the normal derivative of my finite element function. And here the normal, what do I mean with normal derivative? Normal derivative, I mean really that is the normal with respect to my surface. So if this, for example, for a surface problem would be a proper stabilization term. But the analysis is quite involved and quite heavily. But the idea is, again, I extend the L2 norm, or I somehow augment my L2 norm on the surface by certain stabilization terms, and that gives me control over the L2 norm on the entire active mesh. So with that, I would just like to conclude. So we can really do a lot of analysis, and if you're interested, I would be more than happy to talk about that. But we can use this, for example, for a Laplace-Beltrami problem here, not only on an embedded manifold of codimension 1, so that is here a surface PDE, but we can even do it on embedded manifolds on arbitrary codimension. So that would be here basically Laplace-Beltrami problem on a 1D line embedded into a 3D bulk. We can also solve this as well. And we can not only do that for Poisson problem, but we can also do that, for example, if we design certain stabilization terms, we can also do that, for example, Darcy problem on the surface. Remember, the Darcy problem on a surface naturally appeared when solving flow problems in porous media with fractured networks. So we call these fractured networks are basically surfaces which required to solve a Darcy problem there. So we can also do that with certain stuff with our stabilization for a problem. And with that, I would like to conclude. So I provide a lot of error estimate for that. So, but that's now getting too much into the detail. But I'm more than happy to provide you the proper references. But what I want to kind of, or how I want to summarize this talk is that these CutFEM framework is basically, like many others, it's an unfitted finite element framework which uses stabilizations, as a properly or suitable designed stabilization in order to gain or to obtain robust schemes. And those schemes then can be really used in a lot of different cases, from blood flow and aneurysms to flow around turbines or even surface PDEs. With that, I would like to conclude. Thank you a lot for your interest, and I'm really, really happy to take any questions.
All right. Okay, thank you very much, Prof. This was really, really a lot of very, very practical applications, as well as the analysis. of course, I'm hoping that maybe you can share with us your slides after, so that if anybody wants, we can give it to them, especially to see how to derive the a priori error estimates in that kind of sense. But apart from that, this for me has been very, very nice. Please, any other question? If you have any questions, please just unmute yourself and ask your question. Hello, anyone to ask a question? Okay, so
yeah.
All right, got it.
So as you know, I worked a bit with this, but last time I was into this was many years ago, and I remember we only was working with order element 1. So for the Stokes problem, we had to use stabilization instead of using Taylor-Hood. How is this now, or is this evolved into higher order method as well? Do you know anything about it?
Yes, of course. I mean, that's a very good question. That's a very good question. And actually, yes, we have a higher. There also exist stabilizations for higher order methods, and and both for surface problems and for bulk problems. So, for example, for the Stokes problem, you can use any kind of Taylor-Hood, not only second order. And they're mainly, there are different ideas. So, for example, if you're looking, for example, for the Stokes problem in a bulk, in an aneurysm, for example, what you can do is that we have seen this penalization of the first order gradient, the normal gradients for P1 elements. And if you're now doing the analysis, then you see that if you, for example, have all elements of order K, what you have to do, as one simple solution, that you would have to penalize all normal order derivatives up to order K. Yeah, so it's not only the first order normal derivative, but also the second order, third order, and so on. Yeah, so that works very nicely, and then you can show exactly the same error estimates with the same high order upper estimates as we are used to. The only thing which you have to, I mean, that might be sometimes a little bit difficult, or a little bit it will require some implementation work, in the sense that you really have to provide then the Kth normal derivative. There exist other methods, for example, called projection methods or volume stabilization methods, where you can actually avoid these higher order derivatives, but you can basically look at local patches, and then you're doing some you're doing some penalization there. For example, what you can do is that you have, for example, patches are consisting of two elements, and then you're defining an L2 projection into the space of, let's say, K order elements, but they're really defined on the entire patch. Yeah? And then you're having a stabilization parameter, stabilization, which basically looks like VH minus the projection of VH. Yeah? And there are different variations of that. So that and there's even a simpler variation for this, where we can even avoid this kind of projection. So there are really a lot of different tools for that out there. And nowadays we really have developed like a very abstract algorithm or framework, in the sense that we only have like 3-4 properties which we really want to prove. Okay, what we want to do, we in order to prove coercivity, we need to extend the H1 norm, semi-norm. In order to prove conditioning numbers, we want to extend the L2 norm. Yeah? In order to provide interpolation estimates, we want to have certain kind of consistency estimates for those stabilization results. So nowadays we really have only these abstract properties, and then afterwards we're talking about, okay, how does different realizations look like that? And the same also applies also for surface problems. You can do that in the same way. And for example, this normal gradient stabilization I showed very quickly in the end, that is one which automatically works for all stabilizations and for all higher orders immediately.
So is this something? Is it what you did for the continuous discontinuous Galeckin for the surface problem for the biharmonic case? So this is what you did for the higher order penalty.
Yeah, yes, also we have considered both continuous elements and discontinuous elements. So if you have only continuous elements, then you only need to penalize your finite element function in normal direction. So you have basically your surface, and then and you have basically to have surface, and then you have to somehow, I mean, on the surface you know how your finite element function looks like, but you have then to somehow provide some control how your finite element function looks like in normal direction. Okay? And that is exactly what this normal derivative is doing. But if you have, and that is only required here for continuous finite element functions, because there you only need to control the L2 norm basically. There's basically only a problem with the conditioning number estimates, to be honest. But if you want to go to DG, you have a larger problem, because then you really also need this already in the proof of the coercivity results. And then you also not only need the normal gradient, you also need the jump of U and the jump of the gradients of U on those faces. Exactly. And then it looks very much something like you would, for example, do in a biharmonic discretization of a biharmonic equation using DG.
All right, thank you very much. Please, is there any other question? All right, so if there's no other question, then we will end the seminar.